For an AI-based startup, what elements would be essential to provide services related to reinforcement learning?
Great question. First, you want to be sure that you're using reinforcement learning for the right reasons. There are other options as well that might fit similar use cases, and you might want to study them as well. For example, genetic algorithms. These are algorithms that are, instead of being based on animal behavior and how animals learn, they are based on evolution. That's also an interesting class that you might want to explore. You need to define the agent, that is the internal policy and the learning algorithm to improve it. So the environment is everything that is relevant to our problem and that's outside of the agent itself. This environment could be a robotic body of our agent, as well as the physical environment in which it acts, or a simulation thereof. Or it could be a virtual environment, such as an electronic trading system or crypto currencies, together with the whole internet as a source of information, for example. It really depends on what you are building and what sort of use cases you have in mind. The environment really includes everything, including the body of the robot, as I said before, that is outside of the agent. And the agent is just defined by the learning algorithm and the policy. The agent sends its actions that it takes into the environment, and the environment generates observations and rewards for the agent. If the agent doesn't have any prior knowledge of its environment and starts learning directly from it without having a model of, say, such things as, say, Newtonian mechanics, for example, to understand the impact of gravity, then the learning, then we call it model-free learning. The agent is dropped into its environment and learns everything from scratch in this case. Of course, if we give the agent models where we have them, which seems a smart thing to do, we speed up the learning substantially with model-based reinforcement learning. In those cases, the agent then can learn from all previous human experience and theorizing, as well as from its environment. Simulating the environment rather than using an environment in real time directly for training has some added benefits of, like, for example, one, being able to learn in parallel, as one can simultaneously train in thousands of simulated parallel worlds. And two, it can create counterfactual worlds in which things have already occurred that we are trying to prevent, that we don't want to occur in reality, or that are implausible but still possible, but yet never happened thus far. Right? This is sometimes important to learn what to do in situations we've never encountered before. Right? If you want your agent to be robust to circumstances, this is a great idea. Next, the reward function. In economics, known as the utility function. I talked about it before. This is probably the most critical thing to get right. It expresses the value, the ethical values, as well as the business priorities of the people on whose behalf the agent is to act. Let me rephrase this. This is really important. The rewards that the agent earns and how it earns these must represent the values of the stakeholders on whose behalf the agent acts. The rewards can be sparse. For example, if you reward an agent only once the chess game ends, with either negative or positive rewards, then this is a sparse reward, as it doesn't reward any intermediate actions. Rewards can also be periodic, at each time step or at the end of an episode. They can have non-linearities, for example, when there are diminishing marginal returns to one sort of element or in a vector of valuable goods, for example. The Cobb-Douglas function is a utility function that is sometimes used. And you have constant trade-offs between any two elements of outputs that you value, and each element is diminishing in returns. So for example, you might value ever more attention on your in your social network feed, but other things are important too, like decency and helpfulness, etc. And you must, of course, turn every wish into a quantifiable metric that makes sense. The business metrics that you care about go into this utility function. After all that, there are trade-offs that you might have to make. The utility or reward or cost function tells you how to make them, as it projects any vector of concerns and priorities into a one-dimensional scale that represents your preferences. You could say that this same object has too many names. But this has to do with the historical development of these ideas. So different names that you see, the different disciplines from which the ideas here have been influenced. Whatever you call it, choose to call it, utility, cost, or reward function, you must get this one right, so that the algorithm is learning how to behave optimally given your preferences. To accurately represent what you want is the hard part. This can be cleverly achieved with some methods from economics that are out of scope here. Anyway, the next thing you have to worry about is the agent. The agent consists of two parts, the policy and the learning algorithm. For small action state spaces, we can use something called Q function, which is simple, but most often is not relevant. What is special about neural networks here is that it is a neural network is a universal function approximator. This means that it can take the whole state space and approximate the most optimal response at every time, given the utility function over the outputs of the system. I know this is quite technical. No question about that. But from a highly complex state space that has all sorts of nonlinear relationships that would be hard to formulate in an analytical expression. Well, these neural networks are really great. This is all assuming a policy gradient approach, which is compatible with a stochastic policy. A stochastic policy is great in games to keep the opponent from learning your policy, and is great for exploring the state action space as well, because you're taking actions, in a probabilistic way. You're not taking always the same actions, right? So you're harder to predict, and you're also exploring the space of possible actions that way. Algorithms which keep a balance between the exploring new actions and ever-changing, in an ever-changing environment, and exploiting what they already know that works, they do better in the long term. It updates its policy roughly by executing its current stochastic policy, then collecting the rewards, and then if the rewards of the action turn out to be good, it increases the probability of taking this same action ever so slightly. And else, if it was not good, then it decreases that same probability ever so slightly. And so it goes on. A child might try out a new trick on a bike and then it falls, because some slight motor action that it took was not as it should have been. And then the child learns to adjust its behavior and falls less often.